Welcome back. And now we are going to kind of switch gears and look at vectors in a slightly different way. Okay, so I'm going to draw a picture to start. Okay, so imagine that we are given a vector, and I'm just going to draw it in standard position for simplicity. Okay, so here's our vector v. And it says, how could we find its components? So really, we want to be able to represent vectors as like a, b, right? Um, but we only know its magnitude. So let's pretend we know it is like 3 units long. I don't know. I'm just going to pretend this is equal to a number that we know. And then we also know its direction, right? Because the vector is given by its magnitude and direction. So we have these two numbers given to us. How can we find its magnitude or its component form? Okay, well, first thing is to recognize that, let's label that this is our angle theta or our direction theta, right? Um, and so if I think about this vector, right, I want it to go, and actually let me put this in a different color just for emphasis. Okay, so I know that this vector, right, I would move from initial to terminal by a units horizontally, and then vertically I would move by b units from initial to terminal again, right? But this is kind of useful, isn't it, right? So I could relate b and a with theta just by tangent. So tangent of theta is equal to b over a. Okay, that could be useful. Um, but let's see, is there something else that's useful? I also know, right? I know that the vector is magnitude of v in length, and I'm just going to move the v there, okay? So if I wanted to find b, right, I know the hypotenuse and I know the angle, okay? And so I could, set up an equation that says that sine of theta is equal to b over magnitude of v. And then if I solve for b, because that would be unknown to us, that would give us that b is equal to magnitude of v sine theta. Oh, that's actually incredibly helpful. Magnitude of v sine theta. And that uses the magnitude and direction that we know. Similarly, for a, I could use cosine. So I would just do cosine of theta is equal to a over magnitude of v. And then that would give us, if I solve for a again, a is equal to magnitude of v cosine of theta. Okay, so what does that mean for us? It means for us that we can write vector v here as magnitude of v cosine of theta for the horizontal component and magnitude of v sine of theta for the vertical component. And so this is another way of expressing a vector in component form in terms of its magnitude and direction, instead of having having us to specify a and b from the get-go. All right. In addition, I just want to kind of provide some summaries. We have magnitude of v, like that length is a squared plus b squared, right? It would just be the size of the triangle. Coming from the Pythagorean theorem, this theta prime, the direction, okay, we do have to be careful. If we, solve this equation that I wrote up here, right, this tangent theta equals b over a, that's true in principle. But when we solve for theta prime by doing an inverse function, we actually get the reference angle, okay? And then because it is the reference angle, you need to adjust it to the appropriate quadrant. So be careful with that. And now we have some more information, right? We have a is the same as magnitude of v cosine of theta. B as in boy is just be the magnitude of the vector times sine of theta. And so we have these other ways of expressing vector v above, which I wrote up here instead of down below. Okay, so that's what should go down there. So that's the main ideas. Let's see them in action. Okay, so suppose we know that the magnitude of v is that and the direction is that. Express the vector in unit vector form. Okay, well, let's start with component form. Okay, we just got done saying that in component form, this would be magnitude of v cosine theta, magnitude of v sine theta. Okay, so then substitute in the magnitude, okay, square root of 23, and then I do cosine of 7 pi over 6, comma, square root of 23, sine of 7 pi over 6. I should evaluate the angle, and this ends up being a negative square root of 3 over 2. I'm just going to write this here, and then this ends up being a negative 1/2. So then in component form, I would have negative square root of 96, okay, 23 times 3 over 2, comma, negative square root of 23 over 2, okay? So then now in ij form, it would just be negative square root of 96 over 2I plus negative square root of 23 over 2j. And that would be my answer. Okay, moving on to the next example. Okay, ooh, word problems. You were wondering when we were getting into word problems, weren't you? I bet you were. So imagine we have the ground, okay? And then an object is going to be sitting on the ground. And on this object, we apply a 80-pound force. So here is our vector. So this is a force vector that is 80 pounds in magnitude. So this is a magnitude. So the magnitude of F is 80 pounds. And it says pulling on the rope at an angle. Okay, that's our direction. So this is our direction theta is 30 degrees. And then it said represent this force in terms of F and in terms of I and J. Okay, so in total, the force vector is going from the box along this rope. Okay, and so if I look at the force and I break it into components, right, it would be the magnitude of F, cosine theta, magnitude of the vector, force vector in this case, sine theta. And this is going to be equal to 80 cosine 30 degrees, comma 80 sine 30 degrees. And so when I calculate this, this is going to give me 40 square root of 3 and 40, okay, if I leave it in exact form. Okay, and then in component form, or unit vector form, it'd be 40 square root of 3I plus 40j, and I would be done. Yes, it is a context answer. You could say the force vector is da-da-da. I'll let you fill in that. Okay. Last one, ball thrown. Okay, this one's fun. I like this. Okay, so now it's a little different. So imagine, okay, here's the ground. And it says a ball is thrown from a height of 1 meter. Okay, so here's the ball. This is 1 meter. At the time of release, the velocity is given by, okay, so this is saying horizontal and then vertical, right? So it's going diagonally, a little bit more horizontal than vertical, okay? So this would be its velocity vector, okay? And if you needed to label this, you certainly could. You could say this is 12.7 J, and this would be the 27.2 I to indicate horizontal and vertical. It says, so find the initial velocity and the angle. Okay. So angle is the direction. Okay, that one I can do. The initial velocity, okay, this is actually going to be equal to the magnitude of v. Because, or the magnitude of the velocity vector, only because over time that speed is going to slow down, right? There's air resistance and friction and rain and I don't know, flies and everything, so it's going to slow down, right? So we just want to figure out how fast was it going initially. So that's actually maybe an easy question to investigate, but it might be useful just for us to say v in component form is 27.2, 12.7, just to get it out of that unit vector form. From here, what I would do is I'd say, okay, let's calculate magnitude of v. So I would do square root of 27.2 squared plus 12.7 squared. Okay, and if you do this calculation, it ends up being 30.0 meters per second. Oh, okay, that's fine. Now for theta, right? I know that tangent of theta is going to be equal to 12.7 over 27.2. Okay, and then solve for theta by doing the inverse tangent function. So arctangent of 12.7 over 27.2. And if you do this, you get approximately 25 degrees. Okay, and so to wrap this one up, I would include a sentence. It does say round to 1 decimal place, and I did round, so it's actually 25.0. Okay, so I would include a sentence saying, the initial velocity is 30 meters per second, and the angle or the direction of the ball is approximately 25 degrees from the horizontal. Okay, but the big takeaways here are that we can use this component form, or we can find the component form based on the direction and magnitude as magnitude times cosine theta for x and magnitude times sine theta for the y. Okay, and then we have all these other properties. So that kind of summarizes a lot of our learning with vectors.